Hello, my name is Zachery Butler, and today I'm going to be going over differential geometry. Now, what is differential geometry? Well, let's take the title and break it down a little bit. Differential usually has to do with derivatives and integrals. So, derivatives and integrals are calculus. Geometry is the study of shapes. So you can assume that we're going to apply calculus to shapes. But more specifically, differential geometry can be seen as calculus with analytical geometry applied to curves and surfaces. Now, why curves and surfaces? Well, in the world, not everything is flat. You can't measure everything by a plane. There's a lot of three-dimensional things instead of just the two-dimensional planar shapes and curves and such. And even curves on a plane need to be measured. So, for example, a hill. A hill is not a flat surface. You cannot see that in a straight line. It's not a straight line. It is a curve. In fact, it's a parabola. So differential geometry became a big thing in the 17th century with the emergence of calculus. Back in the 1600s, big guys like Huygens, Gottfried, the Bernoulli brothers, Gauss, Euler, Einstein, all of these gentlemen, these great mathematicians, had a big hand in the not just discovery, but the growth of differential geometry. So to begin with, we're going to talk about something called the involute. So first of all, let's draw ourselves a curve. As you can see, I have a diagram here of a curve. We're just going to call this curve C. Now, what is the involute of C? Well, let's imagine that we have a very tightly wrapped rope going all the way down the curve. And if you pick a point on P, a point P on C, so we'll call this P, and you unravel that string but pull it tight, it creates a new curve. This is the involute. Now, the involute is always perpendicular to the tangent at P. So if we have P here and its tangent is, say, something like this, then this is supposed to be perpendicular. Now, it may be a little easier to examine, not just on a 2D plane, but on a 3D space. So, following the involute, if we decide to take more points and create more involutes, we have a series of new curves. So we'll call this new point Q, and this point right here, and its involute R. Now, as you can see, none of them join together. They do not intersect. So that means that they are disjoint. So Christian Huygens was a big name in planar curves, and he discovered this. He saw this, and he actually used this to create a pendulum clock. And whenever you have a pendulum clock, it's like got a big box with your clock. It's got a weighted string pulled tight, and it goes back and forth. And whenever it goes back and forth, there's a little gear in here. It'll pass a certain point, and it'll give a small kick, and it'll continue with the right amplitude and the right length. You can have a relatively precise clock. So he used these involutes to discover that amplitude of the clock. So with an involute, we have an evolute. Now, what is an evolute? Well, the evolute is something, it's very similar, but not quite the involute. So we have our curve again, curve C. We have a point P. Now, every point on the line has a normal line, a normal vector, if you're talking in physics, that is perpendicular to P. Now, if you add more points, such as P, Q, and R, and you draw their normal lines, you'll see that all of these points eventually intersect. Now, this intersection is known as the center of curvature. Now, if we move P, Q, and R anywhere on the curve, it will actually move the center of curvature because these normal lines will change and along with their trajectories, and that will create different centers of curvature. So if we move it and we create more centers of curvature, then what we have is actually another curve that can be created out of those points, out of those different centers of curvature. That is the evolute. Now, so we can call this here, I'm going to move this up here, center of curvature is where the normal lines of the different points intersect. Now the evolute can be defined as the locus, which means the local points joined together of the centers of curvature. So, now as you can see, these kind of work inversely. So, and if you were to actually work it out, you would see that if you take the evolute of an involute, then you are returned with the same curve. So if you were to take the evolute of these involutes, you would be returned with C again. So as you can see here on the diagram, at each point you have points on C, C1 through Cn, and you have other points here of the involutes. These are the evolutes and these are the involutes. It is the exact same curve. By taking the evolute of your different involutes, you get the exact same curve that you started with. So, next we have attractors. Now, what is attractors? Well, let's think of it as you're trying to take your dog for a walk. Your dog doesn't want to go anywhere. So you're the owner. Your dog's right here, and you have a leash. As you continue to walk down the path, that leash begins to move in a different path. Eventually, you start dragging the dog along. The dog will eventually take a route from here to behind you as you continue to walk down the path. The path that the dog follows is known as the attractors. But the dog must start off orthogonal to you perpendicular to your position in order for the dog to create attractors. You can also see it as walking a rock, a pet rock. So next we have the catenary. So what is a catenary? Catenary, many people believed at first that it was classified as a parabola, but geometrically and arithmetically you cannot constitute a catenary as a parabola. So what a catenary is you can see it as a hanging chain. So if a chain is held up by its two extremes, then the curve that the chain creates is the catenary. This was studied by Jacob Bernoulli, one of the Bernoulli brothers, who were in mentorship from Gottfried Leibniz. And their studies of the catenary actually led to the use of suspension bridges. Okay, so far we've talked about what? Planar curves, correct? So now we go from planar curves to space curves. So we all know planar curves are in 2 dimensions. This is a plane. This is a plane. Now a space curve is we go up 1 dimension. So we now have not only the x and y axis, but we have the z axis as well. X, y, and z. Using x, y, and z, we normally the z is a function of x and y. Or you can have a function of x, y, z, and you will get a curve in the 3-dimensional space. You can have smooth curves, and you can have not so smooth curves, but we don't want to mess with the not so smooth curves right now. We're going to focus on the smooth curves. Next we have surfaces. First, we all know that you can find the z of a curve, which is the function of x and y of a curve, using line integrals, which is denoted as integral c. But we're not going to get too far into that today, because it would require a lot of calculus explanations. So next we have surfaces. Now, why do we want to study surfaces? The Earth is a surface, and the Earth is full of different surfaces, different curved surfaces. So one of the main things that the mathematicians at this time wanted to figure out was how to calculate curvature. Curvature, nowadays known as the Gaussian curvature, is denoted by k. Now, back in the day, when they had let's say a little surface like this right here, they originally wanted to divide it into planes, and the projection of the slicing that plane does, so if you put a plane in here, then this little slice right here and the curve that is projected onto this tangent plane of the surface can be found in order to find the curvature. So they essentially cut it in half and took that projection of the cut and used that to find the curvature. Gauss actually found that whenever you do this, you'll have 2 different curvatures: a maximum curvature, K1 or K2, and a minimum curvature, K1 and K2. So, but not one single curvature. Using the angle of the plane, that is the angle corresponding from the plane to the actual curve, the line of the curve of the line, or the line of the curve, he came up with K equals K1 cosine 2 alpha times K2 sine to alpha. Alpha being the angle between the plane and the curve. Now you can also see this as, which is equivalent to 1 over alpha squared. Now through this, they found many different information, much information about the different surfaces, including how to find the curvature of a sphere. So on the curvature of a sphere, if you were to say to take for example, Earth. So we have Earth, it's a sphere. We have a sphere. You want to find the curvature at a point P. Now it was argued back in the day that if you took a smaller circle and tried to find the area of that, well, if you try to find the area of that small circle, it would not equal the actual curvature, it would not actually equal the curvature of the Earth or of the sphere. It would not actually equal, arithmetically, it would not equal the actual area of that circle on the sphere, because area would not equal actual measured, say they measured it actually in feet, etc., because of the curvature. Curvature had to be taken into account. So this is why they wanted to find the curvature so bad. Now, with the sphere has a constant curvature. So sphere, K of a sphere is constant. Now this can be seen as a special case, and they wanted to see what other kinds of things, other kinds of shapes had that exact same constant curvature. We can see that a plane has a constant curvature of 0. Because a plane is flat, it has no curvature, and it's constant across the whole plane, so K equals 0 on a plane. So these were the two main ones that they knew about. But they decided to look further, and they discovered what's called a pseudosphere. Now, a pseudosphere, if you determine the curvature of a pseudosphere, you're not going to be, this was predominantly by Gauss. Gauss did not actually find K1 and K2 of the pseudosphere. He used his formula to find K of the pseudosphere. Now, in order to create a pseudosphere, we'll take that tractrix that we had earlier. Look a little something like this. If you take that tractrix and you revolve it around an axis, you get a reflection that looks something like this. In fact, this is open-ended and it continues to grow smaller and smaller, but never reaches infinity. In fact, they found that this pseudosphere is finite. The surface area and the volume that is enclosed in it is actually finite. So this pseudosphere has a constant curvature. If you look at the tractrix, how it curves inward, it continues at a constant rate of curvature, maybe exponentially or quadratically, but it has a constant curvature. This can be seen as the inverse of a cylinder. All of these different ideas of differential geometry, it continued on not only from the 17th century, but all the way up until even Einstein. In fact, curvature became a very important aspect of Einstein's theories, one of which was that curvature actually affects the space-time dimension. Because we all know Einstein decided to, or not decided to, but discovered that there is a fourth dimension of time. So, in essence, differential geometry created in the 1600s was very influential, and it became the answer to a lot of questions that mathematicians originally had, that they could not solve them algebraically, arithmetically, not without the but the discovery of calculus and differential geometry. So I hope you understand differential geometry a little more. Thank you.